This conference will now be recorded.
Hello everyone. We will start with a problem. Last day we have already started the reagent, which is very important, potassium permanganate. And there is another compound which is very close to the structure of KMnO4, which is K2MnO4. Now the problem here we have that is related to these two compounds. One is manganate ion, another one is permanganate ion. We have to find out the incorrect statement. There are total 4 statements, and among these 4 statements, one of the statement will be wrong. The first statement is in manganate and permanganate ions, pi bonding takes place by overlap of p orbitals of oxygen, d orbitals of manganese. So manganate is MnO4 minus 2. But permanganate is MnO4 minus. That is the difference between these two. So here we can see both are tetrahedral. One is MnO4 2 negative charge. So this is manganate, and when there is one single negative charge, then it is permanganate. Color is different. Now pi bonding and sigma bonding, how it forms, that we have already discussed in the last class. If you look at the green structure, which is manganate, here we have total 4 sigma bond, 2 pi bond. And in the second one, purple color, here we have total 4 sigma bond and 3 pi. Okay. Now here it is mentioned that pi bonding is formed by the overlap of p orbitals of oxygen and d orbitals of manganese. Now pi bond formation takes place by sidewise overlap. Now this sidewise overlap, it may be between 2 p orbital like this, or it may be between 1 p orbital sidewise overlap and another d orbital. Both are possible. So in this case, basically both sidewise overlap between p orbital and p orbital d orbital, both present. So that is why this statement, which is that is saying that overlap of p orbitals of oxygen, d orbitals of manganese. So this is actually correct, though it is not the full information, because the pi bond formation takes place by involving p orbital of oxygen, d orbital of manganese, another p orbital also taking place, which is p orbital of oxygen and p orbital of manganese. Both are possible, but in this statement we cannot say this is wrong, because this is giving us partial information, but still it is correct statement. Just have a look in the previous slide that we have discussed in last class. Here we can see that both pi bond formation is taking place by involving the 4p electron of manganese and also the d orbital of manganese. So there are 2 p pi d pi bond and 1 p pi bond. Okay, so that is why this statement, that will be correct statement. That is the first statement, that is correct statement. So this is true. Next statement is saying manganate ion is green in color, permanganate ion is purple in color. Now this is also true, though here picture is given, but this is a memory based statement that you have to remember. Otherwise it is not possible for us to remember always what is the color. Okay, this is also correct. Third statement is manganate and permanganate ions are paramagnetic. Now how to understand whether a particular compound it will be paramagnetic? It is because of the presence of unpaired electron. So if there is unpaired electron, it will be paramagnetic, but if there is no unpaired electron, it will not be paramagnetic. Now the first ion, that is manganate, which is MnO4 double negative charge. Here oxidation state is +6, and for MnO4 single negative charge, which is permanganate, here oxidation state is +7. Now for the first one, how many d electrons are present, that we will see, and also for the second one. But before that, first see, when Mn is neutral, what is the electronic configuration? It is argon then 3d5, 4s2. Okay, so if there is +6 oxidation state, that means now it will be loss of 6 electrons, 2 electron from 4s and 4 electron from 3d. So that structure will be now argon and then 3d1. But when it is in +7 oxidation state, all the 7 electrons will be removed, and now it is 3d0. So see, in +6 oxidation state you have 1 unpaired electron, but in +7 you do not have any unpaired electron. So here both the ions are not paramagnetic, only one of them is paramagnetic, and that is, which one is paramagnetic? Where you have only one unpaired electron. So 3d1, that is Mn +6, which is basically MnO4 2-, that is manganate. So manganate is paramagnetic, not permanganate. So this statement is incorrect statement. So obviously the last statement will be correct. Both the ions are tetrahedral, that we have already seen in the last class. We have discussed the structure of both these ions in detail. Okay. So here incorrect statement will be option 3. So is there any doubt in this question? Should I repeat it once more? Why it is incorrect? Next is properties of KMnO, that is potassium permanganate. Now this is a very versatile compound. It can react with so many different types of compounds. So that is why its chemical properties are very important. Action of heat. If we are simply heating KMnO4, what will happen? It will decompose, and it will decompose to potassium manganate, K2MnO4, and other products are MnO2 and oxygen. So what will be the products of decomposition of KMnO4? That is important for us to know, because when we will discuss the problems related to this, then you will be seeing that question related to this decomposition, that is also there in the exam. How it reacts with alkalis. Alkali means it may be KOH or it may be NaOH. When we are heating KMnO4 with alkalis, it transforms into manganate ion. So again we are getting manganate ion, and there is also evolution of oxygen gas. Okay. So KMnO4 plus KOH, we are getting water, oxygen, and K2MnO4. Reaction with acid. So after reaction with alkali, next we have to see what is the action of acid. But two different conditions here we have. One is, if you are using cold and concentrated H2SO4, then there will be one type of reaction. If you are using hot and concentrated H2SO4, then there will be different type of reaction. So when it is cold concentrated H2SO4, we get first Mn2O7, this type of oxide. But when it is not the end of reaction, in the first step Mn2O7 that is formed, next step it will now decompose to, if it is warm, it will decompose to MnO2 and oxygen. But if it is hot and concentrated H2SO4, now what we are getting? Now we are not getting MnO2. Instead we are getting manganese sulfate, MnSO4. Okay. So in this way, see, the difference is, if you are using hot concentrated H2SO4, then there is Mn2O7, which is decomposed further to MnO2. But if it is hot concentrated H2SO4, the product, that is the fate of manganese, will be, now it is converted to the sulfate salt, MnSO4. Okay. How it reacts with hydrogen peroxide, that is H2O2. KMnO4, it is oxidizing agent. We know that because Mn is having +7 oxidation state. So it is highly electron deficient. It will always have a tendency to accept electron. Now H2O2, which is basically can act as reducing agent as well as oxidizing agent. But in this case, obviously it will act as reducing agent, and KMnO4, that will act as oxidizing agent. So KMnO4 now reduced to MnO2. And why I am saying that it is reduction? Because now the oxidation is +4. So from +7, now it is +4. So obviously it is acceptance of electron, and electrons are donated by H2O. Okay. Now, if it is in acidic condition, then how it reacts? H2O2, KMnO4, H2SO4. Now the products are different. Now it is MnSO4, where oxidation state of manganese +2. Okay. So depending on whether we are using H2SO4 or not, products are also different. Okay. Oxygen, water, these two are produced in both cases. But when there is H2SO4, now we are getting manganese SO4. There manganese is +2 oxidation state, and also K2SO4 is produced. So these are different chemical properties: action of heat, action of alkali, then action of acid and hydrogen peroxide. We have a question which is related to chemical properties of potassium permanganate. Here 3 equations are given. The first equation is compound A reacting with potassium hydroxide and oxygen. It is giving us green colored compound B and water. Now this green colored compound B, in presence of HCl, it is now producing carbon and sorry, not carbon, it is C. That is unknown compound C. Then MnO2, this unknown compound is purple in color. Manganese oxide and water. Now this unknown compound C, further if it reacts with water and potassium iodide, it is again giving us the initial starting material, which is A, KOH and D also produced. So here we have basically 4 unknown compounds, A, B, C, D. But the question is asking that in the above sequence of reactions, A and D respectively are. So we have to find A and D only, not the other compounds B and C. But though it is asking A and D, but basically you have to understand all the compounds. Otherwise, because it is related. If you do not know what is B and C, you will not be able to understand what is D. Okay. So A options are for A is Ki, MnO2, KiO3 and Ki, that is the first compound mentioned in each option, that will be for A. And options for D is, it is a second molecule. It may be KMnO4, KiO3, MnO2 or K2MnO4. Now, green color compound and purple color compound. Remember, manganate is green color, permanganate is purple color. And in the last class, when we have discussed the preparation methods of potassium permanganate, then we have already seen that starting from pyrolusite, that is MnO2, which is ore of magnesium, by using this pyrolusite ore, some oxidizing agent and some fusion reagent, we can make KMnO4. Now look at the first equation, that is actually the preparation method of KMnO4. But preparation method of KMnO4, it involves 2 steps. In the first step, there is production of K2MnO4, which is potassium manganate. Then this potassium manganate is further converted to potassium permanganate. So the first step, that is the first equation, that is actually the first step of the preparation method of KMnO4. And green color, that is potassium permanganate, K2MnO4, that is green color. So B is basically K2MnO4. Now K2MnO4, in presence of HCl, it produces purple color C. Now this purple color C is KMnO4, that is potassium permanganate. And potassium permanganate C in presence of Ki. Now Ki is source of iodide ion, I-. So I- now will act as reducing agent. So I- will be converted to, that is, it will itself oxidized, and KMnO4, that will be reduced. Now A we are getting back, and A is basically MnO2, because from pyrolusite ore we use for the preparation method of KMnO4. So A is pyrolusite or MnO2. And if you are sure about this, that is, if you know, it is confirmed that A is MnO2. Now see, MnO2 is present only in option 2. So even if you are not sure about the structure of D, and if you are lagging in time, then you can easily choose option 2 if you are confirmed that A is MnO2, because MnO2 is not present in any other option. So MnO2 in presence of KOH and O2, while KOH is fusion, it is used for fusion purpose, and oxygen is basically the oxidative agent. We are getting green colored K2MnO4, which is potassium manganate. Now this potassium manganate in presence of HCl, now it is converted to purple colored KMnO4. And this purple color KMnO4, which is C, now it will be converted to MnO2. So Ki is acting as reducing agent. So that is why from +7 oxidation state, now it is +4 oxidation state. And the fate of I minus, here it is iodide ion, but now it is converted to IO3, where oxidation state of iodine is +5. That means it has lost electron. Okay. So A is MnO2 and D is KiO3. Because see, in the last equation, third equation, A is MnO2, KOH is already written, but D is KiO3. So correct option will be this one. Any doubt?
No, ma'am. No, ma'am.
Next question is also related to this reagent. Thermal decomposition. Let me change the color. Thermal decomposition of Mn compound, that means manganese compound, which is denoted as X at 513 Kelvin. So temperature is given in Kelvin, and this is simple thermal decomposition. We are not using any reagent. You are simply heating the manganese compound, which is denoted as X. We do not know what is X. Now, when you are heating this compound X, which is manganese compound, you are getting Y, MnO2, and the gaseous product. So three things we are getting. We are getting Y plus MnO2 plus gaseous product. Now MnO2 reacts with NaCl and concentrated H2SO4 to give a pungent gas Z. We have to find out X, Y and Z respectively. Now for Z, here we have basically two probability. That is, Z is basically this last compound. The first compound is X, second one is Y. So X may be K3MnO4, K2MnO4, KMnO4 or K2MnO4 again. Y may be K2MnO4 two times or it may be KMnO4. But for Z, chlorine is coming thrice and SO2 it is coming only once. Now one important feature is given for Z, which is pungent odor present. Now both, we know that chlorine is having pungent odor, but SO2 is also having same kind of pungent. So just based on this information, it is really difficult for us that whether it is chlorine or SO2. So better we focus on X and Y. Now thermal decomposition of KMnO4 that we have discussed in today's class. Remember in chemical properties, and there what we have seen that when KMnO4 is decomposed, there is production of three things. One is K2MnO4, MnO2 and also gaseous. So Y is basically K2MnO4. Now K2MnO4 as Y, that is present in option 1 and 3. So we can cancel 2 and 4. Okay. Now among 1 and 3. Next, if you want to know what is X. Now this Mn compound X, it cannot be K3MnO4 because K3MnO4 this type of compound doesn't exist. But and Y is K2MnO4 that we have already chosen. So only one option is left if this is not possible, because 2 and 4 we have already cancelled. Among 1 and 3, now K3MnO4 is also cancelled. That means this is left. That is the option that is left. Okay. So that is why X will be KMnO4, Y is K2MnO4, and Z is K. You see, when X is heated, we are getting Y, which is K2MnO4, MnO2 and the gaseous product, which is oxygen. And MnO2, when reacts with NaCl, concentrated H2SO4, MnO2 is basically acting as, here Cl is present as chloride, right? But after reaction, it is 0. So from -1 oxidation state, now it is 0. So it means it is loss of electron. And MnO2 from +4 state, now it is MnCl2 +2. So this is gain of electron. So here Cl- is oxidized, Mn is reduced. Okay. So Z will be chlorine, and correct option is X KMnO4, Y K2MnO4, and Z is option 3 is the correct option. Is it okay?
No, ma'am.
Should I repeat it?
No, ma'am.
Now some more properties of potassium permanganate, and the most important property is oxidizing property of KMnO4. Now this is not very simple, because depending on what type of medium you are using, that is it acidic or neutral or alkaline, depending on that, products will also be different. KMnO4 can oxidize many inorganic compounds, and not just inorganic compounds. You will also see that KMnO4 is used as oxidizing agent even in organic chemistry. Okay. Medium of the solution is very important here, because depending on that, products will be different. Oxidizing power of KMnO4, it is maximum if you are using acidic medium. Remember, this is very important question. It can be asked that in which medium KMnO4 will show maximum oxidizing capacity, and the answer is it is acidic medium, because in acidic medium only it accepts maximum number of electrons. Now oxidizing power means what? Acceptance of electrons. Now more is the number of electrons accepted by any compound, higher will be the oxidizing capacity. And in acidic medium, it is accepting maximum number of electrons, and that is the reason why it's acidic. In acidic medium, its oxidizing capacity is maximum as compared to basic and neutral. So when it is acidic medium, MnO4 minus, here we have not mentioned potassium because that is not required. Just focus on this ionic equation. From +7 oxidation state, after reduction, that is gain of electron, because it is accepting electron, now it is converted to +2. So from +7 to +2, obviously it is 5 electron. And to balance oxygen both sides, because left hand side you have 4 oxygen, so right hand side, how you will balance it? Just add 4 H2. And as we have added H2O, now you have total 8 hydrogen, that we can balance by placing 8 H plus. And you can write H plus because it is acidic medium. Okay, if it is basic medium, you cannot write H plus. So in this method, actually we use when we balance half reactions of in redox chapter, this type of method we use. Okay. If it is neutral media, then what happens? Now in neutral media, MnO4 minus is converted to MnO2. That means +4 oxidation state. So from +7, if it is achieving +4 state, it is gain of 3 electrons. So see, this is 3 electrons. We are balancing oxygen by writing 2H2O, because already 2 oxygen here. So total 4 oxygen, and as we have mentioned 2H2O, so 4H we have to write as H plus. Okay, so though it is neutral media, but here we have written H plus because it is ionic equation, so it seems as if it is acidic medium, but actually it is not. Okay, and if it is basic medium, Then MnO4 minus is converted to manganate ion, MnO4 minus 2. So from plus 7 now it is plus 6. That means it is simply gaining 1 electron. Okay. Now we have here different examples of KMnO4 which is acting as oxidizing agent, and all these examples are specifically in acidic medium. Okay. And these equations are basically ionic equation. It is not molecular equation. Molecular equation means where we have only neutral molecules, but here it is ionic equation, so we will have ions only. Iodide ion, it may be NaI or Ki. In presence of MnO4 minus, it is converted to iodine. So from -1 state, now it is 0, that means it is loss of electron. And MnO4 minus, that is converted to MnO. So see, this equation written in orange color, here final compound is Mn2 plus. So that is the common thing you will find in all these equations. See, Mn2 plus is common. It is always produced because it is acidic medium. So whatever is the nature of the reducing agent, it may be I minus, oxalate ion, sulfite ion, nitrite ion, sulfide ion, Fe2 plus ion. So whatever is the reducing agent you have taken, but as it is acidic medium, so the fate of manganese, it will always be Mn2 plus. Okay. So in the first equation, iodide is converted to iodine, and then second equation C2O4, that is oxalate ion. Oxalate ion, if you add 2 hydrogen, the structure is like this: CO2H, another CO2H. This is C2O4H2. But if you remove 2H, it will be CO2 minus CO2 minus. That means C2O4 minus. So it is now converted to carbon monoxide. Then SO3 minus, sulfite. It is now converted to sulfate. NO2 minus, nitrite. It is now converted to nitrate. In nitrate, oxidation state of nitrogen is +5, but in NO2 minus, it is +3. That means from +3 to +5, it is loss of electrons. So it is oxidized by MnO4 minus. Then H2 minus ion, it is converted to 0. So again loss of electron. And Fe2 plus converted to Fe3 plus. This is also loss of electron. Okay. So these are examples of KMnO4 acting as oxidizing agent, but in acidic medium. If it is neutral medium or faintly alkaline medium. Now remember, it may be neutral or very weakly alkaline. Then the final, that is the fate of MnO4, though I have not mentioned it here, but actually it is applicable, that is the equation written in black color, it is applicable both for neutral as well as weakly basic medium. But if it is strongly basic medium, then you have to follow the blue colored equation. So when it is faintly alkaline or neutral, the fate of manganese is MnO2. See, this is common. And what type of reducing agent we are using? Thiosulfate ion, H2O3 minus, it is converted to sulfate. Next equation, again we have used iodide. Iodide is now converted to KiO3. Now one interesting thing you can see here, examples of acidic medium, all these equations. Look at the first equation. Here we have used iodide, and for neutral and faintly alkaline, here also we are using iodide, but products are different. Here I minus is converted to iodine, that is from -1 oxidation state, it is achieving 0 oxidation state. But in this case, it is converted to iodate ion, that is IO3 minus ion. Our oxidation state is +5. Okay. Then we are using H2S, which is nothing but source of sulfide ion. See this equation. Here sulfide is converted to S. Here also it is converted to sulfur. But Mn is always converted to manganese dioxide. So these are examples in neutral or faintly alkaline medium. Mostly you will see, as oxidizing power of KMnO4 is maximum in acidic medium, so most of the examples are under this category. Here we also have one example. If it is strong alkaline medium, we have taken SO3 2-. See, this is also SO3 2-. Here also it is converted to sulfate. That is same fate we are observing for SO3 2-. But KMnO4 is now converted to K2MnO4. See, this blue equation, it is MnO4 2-. So this is also MnO4 2-. Fine. Any doubt? Now some more oxidizing actions
No,
of MnO4 we will see. Any doubt?
no, ma'am.
So okay, these examples are basically you will find in organic chemistry. It can oxidize carbon atoms that have double bonds, that is CC double bond unsaturation if it is present in organic compound. Then it will be converted to CH2OH, CH2OH. So this is ethylene, right? And after reaction, it will be now CH2OH, CH2OH. Okay. Dihydroxylation because 2OH is added. Here unsaturation is now removed. So in this equation is actually used for identification of CC double bond. That is, if there is any unsaturation present or not, that you can identify by using KMnO4 reagent. So suppose you have any unknown sample of organic compound and you do not know whether it is unsaturation is present or not, but you want to identify. Then what you will do? You will add some KMnO4 reagent. If unsaturation is present, now unsaturation will be removed, and as a result KMnO4 it will also be reduced. Now when KMnO4 is reduced to MnO2, obviously the purple color will no longer be present. So when the purple color is discharged, it will prove that CC double bond or triple bond unsaturation is present. So this is very important test for identification of unsaturation, because whenever we do any identification test, you have to keep in mind there must be some visible change. It may be color change, it may be precipitation, it may be evolution of any gas which has specific odor. So all these are some changes that you can easily identify. So in this case, purple color of KMnO4, which is very intense color, it will be discharged. So it is the proof that KMnO4 is acting as an oxidizing agent, and CC double bond now it is no longer present. It can also oxidize aldehyde, that means RCHO. So this is aldehyde, and after oxidation by KMnO4 it will be converted to carboxylic acid. That means now it will be converted to RCOOH. So this is oxidation by KMnO4. It can also oxidize carbon atoms that have triple bond. So when it is CC double bond, you are getting dihydroxylation. But suppose if we have triple bond, both sides there is any group. Now after addition, what we will get? Dione. Dione means keto compound, diketo, like this. So here also basically the CC double bond now it is no longer present. It can oxidize sugar and it can convert it to acid by breaking the carbon skeleton at the double bond. Fine. So these are the examples of organic chemistry where KMnO4 is used as oxidizing agent. Application of KMnO4. It has versatile application. Okay. In laboratory and industry, it is used as oxidizing agent, and then in volumetric analysis for the estimation of ferrous salt. So volumetric analysis means suppose it is actually quantitative estimation, not qualitative, because ferrous salt, that is Fe2 plus salt. So suppose you know that you have some Fe2 plus salt, but if you want to know actual amount, that is quantity, Then what we do, we use KMnO4 because KMnO4 can convert Fe2 plus to Fe3 plus. So if you know the concentration of KMnO4 and concentration of Fe2 plus is unknown, now when it will react with KMnO4, the amount of KMnO4 that will be used from that amount, because you know what is the volume of KMnO4 you are actually using for this oxidation, and concentration of KMnO4 solution is also known. So from this known information, you can easily find out what is the actual amount of Fe2 plus. And this is volumetric analysis for estimation of ferrous salt. Not just ferrous salt, it may be oxalate ion C2O4 minus, it may be iodide, that is I minus salt, or it may be H2. So all these compounds for their quantitative analysis we can use KMnO. This is very important application. Then it is used to detect halides, oxalate, tartrate and sulfite, because in all these cases it will act as oxidizing agent, and all these compounds, that is halide, it will be oxidized, oxalate will be oxidized. So there will be some change which will help us to understand that for the detection of these ions. Used as water disinfectant and employed in dry cell, employed in bleaching of wool, cotton, silk and other textile fiber. So very large application we can understand from this table. Okay. Now we will see how we can use KMnO4 in redox titration, and this is basically the second point in the application box. See, I'm talking about this volumetric analysis. Here we have mentioned that we can use it for estimation of ferrous salt. Basically, all these are involved in some redox titration, and that point we are going to discuss. But before starting, we have to understand what is redox titration. Now the term redox, it is basically combination of two terms, reduction and oxidation. That means both these will take place simultaneously. If it is A plus B, that is two reagents are reacting with each other, so one will be reduced, another will be oxidized. It is a laboratory method for determination of concentration of a given analyte by causing redox reaction between the titrant and the analyte. So here you can see two words. One is analyte, another one is titrant. So suppose there is reaction between A plus B. Now concentration of A, it is known, but B is not known. And you want to know what is the amount of B that is actually present. So if you know the concentration, that is actually will give you the idea how much B is actually present. Now A is known, B is unknown. So the reagent which is unknown, not reagent, that is the reaction partner which is unknown, that is called analyte, and the reaction partner whose concentration is known, it will be called titrant. That is the difference. It is one of the most common laboratory method to identify the concentration of unknown analyte. So what is titrant and what is analyte? Here it is mentioned. Solution of known concentration which is added to another solution whose concentration you want to identify. And what is analyte? There is another term for analyte, though it is not used. Mostly we use the term analyte, but it is also called titrant. See the difference in spelling. This is T, this is D. So what is analyte or titrant? The solution for which you are trying to identify the concentration. Okay, so this is the difference between these two terms. So determining the concentration of an analyte, here our titrant will be KMnO, and the analyte, that will be all those ions. Remember in the last slide we have mentioned oxalate, iodide, ferrous salt, that is Fe2 plus, all these will be analyte. Redox titration can accurately determine the concentration of an unknown analyte by measuring it against a standardized titrant. Standardized titrant means you know the concentration of titrant. That is why it is standardized titrant. So KMnO4, it is very common example in the redox titration of titration. So KMnO4 is the titrant here. So you know that is the KMnO4 solution that you have taken. You know what is its concentration. Okay. And the titration is of KMnO4, it is done against an analyte, which is unknown, suppose unknown compound of Fe2+. That is Fe2+ is present, that is fine. But what is the amount of Fe2+ that we have to find out. And Fe2+ source is more salt. More salt formula is given here. It is ferrous ammonium sulfate, hexahydrate, because 6 water molecules are there. So here we have 2 NH4+ ion, 1 Fe2+ ion, and 2 sulfate. Now if you see total positive charge 2 NH4+, that means 2+, this is also 2+, so total 4+, and total negative charge 2 into -2, -2. So overall molecule is neutral. So this molecule is used as the source of Fe2+, and this is known as more salt. Fine. So this is the system, and that is the titration. It looks like this, where we take conical and we take burette, and in burette there is KMnO4 solution we have taken. Now from this scale you will be able to understand how much KMnO4 you have used. Okay. And in the conical there is unknown analyte. So in this case there will be Fe2+. Okay. The use of KMnO4 as titrant is particularly useful here as it can act as its own indicator. We know that in titration we need some indicator which will change its color, and from that change in color we'll be able to understand when the reaction is complete. But in this case you don't have to use that is any extra indicator, because KMnO4 it is having already a specific intense purple color. That means the KMnO4 that you are using, drop wise it is coming from the burette and it is falling here, right? But after some time it will lose its color. That means KMnO4 is already converted, it is reduced to some other species. So that is why its purple color is no longer present. So it is the self indicator. That is the reaction partner, that is the titrant in this case, that is already, it is doing two things simultaneously. One thing is we are using it as standardized titrant, and second role it is playing is it is acting as indicator also, because it has specific color, and after reaction it is colorless. So when it is becoming colorless, that means reaction is going on. But during the titration, as time that is as the reaction is proceeding, one time will reach when the color will still persist. In the last conical you can see the color is still there. That means further KMnO4 when you are adding, there is no Fe2+ present. So suppose all Fe2+ now converted to Fe3+. But if there is no Fe2+, obviously the KMnO4 that you are pouring from burette, that is still KMnO4. There is no reducing agent. So that is why now you will be able to understand that the reaction is complete. So it is possible to detect the endpoint of titration without using any indicator, because the solution will remain slightly purple. Slightly purple because unreacted KMnO4 is there. And this type of reaction is possible because other reaction partner, which is Fe2+, it is itself colorless. Suppose Fe2+ is also having some color, KMnO4 is also having some color, then there will be some confusion. But in this case, that is A plus B. A is KMnO4, B is Fe2. So B is having no specific color, but A is having some specific color. So that is why it is possible. So here Fe2+, that is converted to Fe3+. It is also donating electron, and MnO4- that is converted to Mn2 plus. Okay, so this is the half reaction, but we can balance this equation by that is adding some water molecules or H plus or electron. And here oxidation state is +7. That means it will accept 5 electrons. Okay. Here we also have the overall equation which is written, but before that, that is how we are achieving this equation, how we will be able to understand. See, this is very easy. Here we have MnO4 minus Mn2 plus. That means 4 oxygen. Now how to balance it? Just add 4H2. Now 4H2O, that means 8H plus present. So here we have to write 8H plus, it is in acidic medium. Now both side hydrogen and oxygen atom numbers are same. But see, here we have 5 electron, but here we have only 1 electron. So these two half reactions, if we want to add and to get the overall equation, then electron number must be cancelled. But here we have 5 electron, this is 1 electron. So what we'll do, we'll multiply this with 5. And then we will add these two equations. So it will be 5 Fe2 plus 5 Fe3 plus 5 electron. And if you are adding this, both sides this 5 electron will be cancelled. And the remaining equation will be MnO4 minus 5 Fe2 plus 8H plus I'm not writing electron because it is already cancelled. 5 Fe3 plus Mn2 plus 4H2. So this equation is mentioned here. See, MnO4 minus 5 Fe2 plus 8H plus, and in the right hand side Mn2 plus 5 ferric ion and 4 water molecules. So from first just write the half equations, then balance the oxygen and hydrogen atoms both sides. Next step is we have to arrange the equation in this way so that in both reactions number of electrons are same, because then electron will be cancelled and you can get the overall equation by just adding these two half equations. Okay, any doubt? Now the KMnO4 that we have used in the previous slide, its concentration is known, but how we will know its concentration, because it is not primary standard. Primary standard means with time there are some reagent whose concentration remains same, but there are some reagents, if you are, suppose you are preparing this, if it is not freshly prepared, that is if you are keeping it for a long time, its concentration will change with time. So KMnO4 is such type of standardized solution where it is changing with time. So that is why just before this estimation, that is supposing if you are doing the analysis of Fe2 plus by using KMnO4, then you have to know properly the exact strength of KMnO4. Okay, so how to do it? For that you have to determine first what is the actual concentration of KMnO4, and for that purpose we will use another known solution of another reducing agent where its concentration is properly known, and that reagent is oxalic acid. It will act as reducing agent. So oxalic acid acts as reducing agent and KMnO4 acts as an oxidizing agent. Here we will again use acidic medium because this is the medium where it shows maximum acidic property, and the acidic condition we will create by using dilute sulfuric acid. So this equation is two half equations. So the same method you can use that we have done in the previous slide. See, this equation is same equation that we have already written, but now the other system is different. It is oxalate ion which is converted to CO2 and 2 electrons involved. Here 5 electrons in. So how to make it equal? What you have to do? Just multiply 2 both sides for the first equation, multiply 5 both sides for the second equation. After that, you can add these two equations and you will get this overall ionic equation. It is ionic equation. Why? Because ions are involved. These are not neutral species. But you can also write the molecular equation, which is like this. So it is 3. And oxalic acid, it also contains water molecules. So that is why dot 2H2O written. And here you will see this Mn2 plus, this is actually this one, MnSO4. Okay. And when you will write the molecular equation, starting from ionic equation, some number may change. So see, here we have 8H2, but here it is 18H2. So this will happen. CO2 number, it is same. There is a new species which is K2SO4 because the H plus that you are using, acidic condition, the source that you are using is dilute sulfuric acid, and sulfuric acid means what? Sulfate ion will be there. And KMnO4, K we have not written, but K plus is also there. So the K plus and the sulfate ion from H2SO4 together, it will make this potassium sulfate. But mostly ionic equation is enough to understand that is how many moles of MnO4 minus is reacting with oxalate. So see here 2 moles of MnO4 minus, that is equivalent to 5 moles of C2O4 minus. Okay, so if you, that is from this ionic equation, you will get this information. Even you don't have need to write the molecular equation, because when you will solve any problem and if it is mentioned, that is if concentration of MnO4 is given or concentration of C2O4 is given, from this relationship you can find out what will be the unknown concentration of the other species. So if concentration of C2O4 is given, you can easily find out the concentration of MnO4. So 2 moles of permanganate reacting with 5 moles of C2O4 minus. That means if it is 1 mole of permanganate, now it will be equivalent to 5 by 2 moles of C2O4 minus. Okay, any doubt? So in this way we can determine the strength of KMnO4, because oxalic acid, it is a primary standard solution where if you are preparing this solution, you can keep it for a long time. Okay, it will give you, that is its concentration will not change with time. But KMnO4, its concentration changes with time. So that is why just before the estimation of more salt, you have to first find out exact concentration of MnO4 minus, and for that purpose you will use the solution of oxalic acid. Okay, any doubt? Here we have a problem which is related to this that is titration. KMnO4 reacts with oxalic acid according to this equation. So this equation we have just seen in the previous slide, right? Here 20 ml 0.1 molar KMnO4 is equivalent to, so see in the last slide what I have mentioned, that 2 moles of MnO4 minus, that is equivalent to 5 moles of C2O4. So now it will, this relationship will help us to solve this question. 20 ml 0.1 molar KMnO4. Now from this information you can easily find out what is the number of millimoles of KMnO4. So when volume is given in ml and concentration is given molarity 0.1, how we will find out the number of millimoles? Simply multiply the volume in ml with the concentration, and this is equal to 2 millimole. Okay, now 2 millimole of KMnO4, remember the relationship, 2 MnO4 minus is equivalent to 5 moles of C2O4 2 minus. So if it is 2 millimole of MnO4 minus, that must be equal to 5 millimoles of C2O4 minus. Okay. Now from which of these options A, B, C, D you can get 5 moles of C2O4 2 minus, that you have to find out. Here the equation is again written. The same thing is given that I have just mentioned. 2 moles of MnO4 minus, 5 moles of C2O4 minus, and 20 ml of 0.1 molar KMnO4, that is actually equal to 2 millimole. Which how you can get? Simply multiply these two. Now from the first option, if you multiply these two, it will be 50 into 0.5, which will not give you the value 5. Then if you multiply these two, it will give you the value 2 millimole. This is also not correct because we need 5 millimoles of C2O4. Third one, 20 into 0.5. This is also not equal to 5. But the last one, 50 into 0.1, this will give you 5 millimoles. So this is the correct option. Last one. Any doubt? Should I repeat? And it may be vice versa. That is, if concentration of C2O4 given, you can also find out the concentration of K. Next problem. Potassium permanganate acts as oxidizing agent in all these three conditions that we have already discussed in today's class. You have to find out the final products obtained from it in all these three conditions respectively. So the first species in each option, that will be the product for neutral medium. Second species, that will be the product for alkaline medium. And the last species, that will be the product for acidic medium. So we need all the equations. So here we have all the equations. The orange color, that is for acidic medium. The black one for neutral or faintly alkaline medium, and the blue one, it is in basic medium. So the first molecule in each option, that will be for neutral, and in neutral it is MnO2, in acidic it is Mn2 plus. So you can easily cancel out this option. Mn3 plus is not possible, and in basic medium it is MnO4 2 minus. Now see, though it is mentioned alkaline, but it is not exactly mentioned whether it is weakly alkaline or strongly alkaline, because depending on weakly alkaline or strongly medium, strongly alkaline products are different. Okay, but neutral, it is if it is neutral, it is always MnO2. So neutral, if it is always MnO2, you can easily cancel these two, right? And you also already cancelled C, so only one option is left, which is B. So though it is not exactly mentioned whether it is weakly alkaline or strongly alkaline, then also you can answer the question, because C option is already cancelled. A and D cancelled because neutral medium MnO4 2 minus MnO we cannot get. So B and C left, but C is already cancelled. So that is why option B will be the correct option. So see here, neutral is also MnO2. Alkaline, though it is not mentioned exactly whether weakly, but it is actually faintly alkaline, which is clear from the answer. And acidic, it is always MnO2, right? So we will end here. Is there any doubt regarding all the slides in the whole class? So if there is no doubt, we will end the session here. Thank you for listening.